All right, I'm going to go through the pre-calculus review and give some hints on some of the problems, or maybe some reminders. Okay, on number 1, find an equation for the line through the point 3, 4 that is both parallel to 3x minus 2y equals 5 and perpendicular to 3x minus 2y equals 5. So 2 separate problems there. And your answers should be in 2 forms. So just a reminder, for A, parallel lines have the same slope. And for B, perpendicular lines have slopes that are negative reciprocals. So I would say that you probably want to start by finding the slope of this line and then you can use that slope with point P for part A, and then you can use the negative reciprocal slope with point P for part B. I've also identified the 2 different forms here at the bottom, slope-intercept form, y equals mx plus b, and standard form, ax plus by plus c equals 0. Okay.
Miss Bryant, I have a really quick question.
Okay, number 2. So we're given a function, f of x is the absolute value of x minus 3, and we want to state the domain, range, x and y intercepts, and sketch the graph. Okay, so let's think about how to, I think often when you're asked questions about graphs and information about a function, it's easiest to actually do the graph first, and then often you can just get the rest of the information, the domain, the range, the x and y intercepts, from looking at the graph. So let's see if we can figure out, what does this function look like? Okay, so first of all, you should, when we think about the domain of this function, well, that should always be a concern when you're drawing a graph. Obviously, if we plug a 3 in there, what's going to happen? We're going to get the absolute value of 3 minus 3 over 3 minus 3, which is 0 over 0. So that is, f of 3 is undefined. But what about any other number? For instance, what if we plug in a 4? If we plug in a 4, that's going to be the absolute value of 1 over 1. If we plug in a 5, that's going to be the absolute value of 2 over 2. If we plug in a 6, we're going to get the absolute value of 3 over 3. All of those are going to give us an answer of 1. So basically, what's going to give us an answer that's not 1? Well, the absolute value of a number is the same as the number as long as it's positive. So as long as the numerator is positive, the numerator and the denominator will be the same. As long as x minus 3 is positive, the numerator and the denominator will have the same value. Well, x minus 3 is positive anytime x is greater than 3. Anytime x is greater than 3, then f of x is going to equal the absolute value of some number over the same number, which is going to equal 1. Well, what about if x is not greater than 3? What if x is less than 3? So what if we have f of 2, which is going to be the absolute value of negative 1 over negative 1. Well, that's 1 over negative 1, which is 1, right? Let's try f of 0. I'm going to get the absolute value of negative 3 over negative 3, or let me fix that. 3 over negative 3, which is negative 1. So now what I'm saying is, if x is less than 3, then I'm going to get f of x equaling negative 1. Okay? And so what does this graph look like? Anytime, here, let's highlight the two things we're using here. Start here. Anytime x is greater than 3, y is 1. So y is 1. What does the graph of y is 1 look like? Well, that's a horizontal line at 1, right? But we only want that graph when x is greater than 3. So I only want that graph over there. And then anytime x is less than 3, y is negative 1. So that's going to be less than 3, negative 1. Let's draw that a little more nicely. There we go. And then the last thing we need to account for is the fact that we know that when x is 3, the function is undefined. That means there's no point there. The graph doesn't exist there, so we need to put holes there. So this is a picture of the graph of our function, f of x, and now it's very easy to answer the other questions. What are the domain and the range and the intercepts? Okay, the domain. That is asking, what can x be? And x can be anything except 3. So I've written here all real numbers except 3. Okay? What is the range? What can y be? Well, the range only has 2 values. The only thing y can be is 1 or negative 1. There are only 2 values in the range. X-intercepts, we're looking at the graph. There are none. And lastly, y-intercepts. You can see there's a y-intercept, and that is 0, negative 1. That is this point right here. Okay. All right. Here's another graph for you to work on. If you saved all your papers from previous courses, you might want to get out your rational function notes, and I'll just kind of set you up here for what you're looking for. For rational functions, first you're going to look for holes. You're going to look for zeros. You're going to look for vertical asymptotes. You're going to look for, what else are you looking for? Y-intercept. You're going to look for non-vertical asymptotes. And I would do a sign chart after that. if you have some old notes, you can dig out the paperwork on that. Wholes, this is the same factor in the numerator and the denominator. Zeros, that's 0 in the numerator only. This is vertical asymptotes, or when you have a 0 in the denominator only. Y-intercept, that's when x is 0 in the equation. Non-vertical asymptotes. Well, as we have already started this, I will give you the calculus way to find this, and that is the limit as x approaches positive infinity and the limit as x approaches negative infinity. And we just learned how to do that. And then a sign chart, use your vertical asymptotes and zeros. And that should be enough to help you draw a graph. Okay, even and odd functions. Just a little refresher on even and odd functions. So an even function is a function like cosine. An even function has y-axis symmetry. And for an even function, f of negative x is equal to f of x. Okay, so let me use cosine as an example. I'll draw a picture. Okay. So you can see that we have y-axis symmetry here. And also, if I could take a data point, so for example, I know that if I look at the cosine values at pi over 3 and negative pi over 3, they're going to be the same. This point over here is pi over 3. The cosine of pi over 3 is 1/2. And then this is negative pi over 3, also 1/2. So that illustrates this relationship. There's one example of that working for the cosine function. Okay. Now, an odd function has point symmetry with respect to the origin. And an example for that would be the sine function. Also, f of negative x is the negative of f of x. Okay, so let's draw a picture of the sine function. Okay. Okay, so there is the sine function. Let's do here. Okay, so I've just picked a couple of points here. So first of all, point symmetry with respect to the origin means I can rotate this 180 degrees and I'll get the same graph. Turn it upside down and you get the same graph. But I'll just pick a point here and I'll show you that this point is 2 pi over 3, the sine of 2 pi over 3, which is root 3 over 2. And then if I pick the point at negative 2 pi over 3, I get negative 2 pi over 3, and the sine of that is negative root 3 over 2. And there's one point that illustrates this relationship for the sine function. Okay. So if you're asked to prove if two functions are even, odd, or neither, you want to do that algebraically if you have an equation. So you want to find f of negative x even if f of negative x is the same thing as your original function, odd if f of negative x is the negative of your original function. Okay, so moving right along here, okay, so just some basic log and exponent rules for the next couple of problems, okay? So let's just, first of all, the relationship between a log function and an exponential function is the, if y equals the log base b of x, that can be written as b to the y equals x. That is the basic relationship between the log form of an equation and the exponential form of an equation. And that should get you through at least the first couple of problems. Okay? Some other basic rules that you might use are the basic log rules. The log of a times b equals the log of a plus the log of b. The log of a quotient, a over b, equals the log of a minus the log of b. And the log of b to the n equals n log b. And these apply to any kind of a log, a natural log, any kind of a log. Okay, so that should get you through number 5. And then the exponential growth and decay rules. So there's a couple of different kinds of rules. So the rule for exponential growth or decay, or compounding interest in discrete units of time, is actually I'll use y here. The amount you're going to have at the end of some time period is equal to your original amount times 1 plus the rate to the t. Okay, now, in this case, r and t must have the same time units. Meaning, if r is an annual interest rate, t must be in years. And you can also look at continuously compounding interest. and we'll actually prove this formula later. And that says the amount you're going to have at the end of some time period is the amount you start with times e to the RT. That's the irrational transcendental number e. Okay, so let's have a look at this problem here. How long will it take an investment to double itself if interest is earned at a rate of 3.25% per year compounded quarterly? Okay, so if we think about this, this formula, a sub t equals a sub o, 1 plus r to the t, then what's going on is this is an annual rate per year compounded quarterly. So that means you're getting interest every quarter. Are you getting 3.25% every quarter? No, because that's the annual rate. You're getting a quarter of that. So your rate is going to be, well, first of all, 3.25% as a decimal is going to turn into 0.0325. So our rate is going to be 0.0325, but divided by 4. And we want our amount to double. So I don't know what amount I'm starting with, and that's okay. You don't have to know what amount you're starting with. But all I know is, in the end, I want to have 2 times that amount. Okay, remember, we're only getting a quarter of that interest every quarter. And we're trying to figure out how long that's going to take. So the first thing I'm going to do is I'm going to divide out the a sub 0. I should also make a note here that at this point, because this is a quarterly rate, time is being measured in quarters. Okay, because remember, this is annual. So now I'm going to, the first thing I'm going to do is divide out the a sub zeros, and then you're going to need to use logs to solve that problem. And for this problem, I said it was okay to use a calculator. All right, so you can go ahead and work on that one. We've talked about domain and range. So I will say that when you talk about domain, I want you to, even though you're asking what can x be, I want you to think, what can't x be? Okay? What can't x be? And exclude those values from a domain. And so for when you're considering that, what should you be thinking about? You should be thinking about, you cannot have a 0 in the denominator. That's number 1. And number 2, you cannot have a negative number in a even root. Equals 8x plus h squared plus 1, right? I put x plus h in there. and then minus f of x. So then you're going to go back up here, simplify the numerator, then divide by h. Okay. Okay, I think the next couple you're going to be able to do on your own, maybe a little looking up. Review of the unit circle. The last one I will give you a hint on is 13. 13 is a factoring problem, really. So I want you to think of, at least the last page. All of these are kind of the same. So all of them on 13, let's go through this one. I want you to think of this as A, and this is B. And if you look over here, then this is also A, and this is also B. So let's say I do a little side work, and I think of this as 6a to the fourth b squared minus 15a to the fifth b. Can I factor that? Sure. I can take out a 3, an a to the fourth, and a b. And what am I left with? So I'm factoring that out of each of these. Okay, so I'm back to factoring this. Sorry for the interruption. So I'm going to take a 3, an a to the fourth, and a b out of each of these terms. So out of the first, if I take that out of the first one, I'm going to be left with, I take out a 3, I'll be left with a 2. The a's are gone, and I'm left with a b. And then over here, I'm going to have a 5 and an A and no B left. So I'm going to do the same thing for this problem. So my 3, A to the fourth is x squared minus 8x to the fourth. B is 2x minus 3. And then here for 2b minus 5a, I'm going to have, let's see, 2b, 2x minus 3, minus 5a, x squared minus 8x. Okay, I'm going to simplify what's here by multiplying it out and combining my like terms. So I'm going to have 4x minus 6 minus 5x squared plus 40x. So right now I have 3, x squared minus 8x to the fourth, 2x minus 3, and then all of this that I just multiplied out simplifies to 44x minus 6 minus 5x squared. Okay, lastly, this is a small detail, but a good thing to catch. You can take an x out of here. Now, this is like x minus 8, all of that to the fourth. That means this is the same thing as x to the fourth, x minus 8 to the fourth. Okay, so now my final answer is 3, x to the fourth, x minus 8 to the fourth, 2x minus 3, 44x minus 6 minus 5x squared.